Hello and welcome. In this video, we'll be covering section 6.2, which is over the applications of right triangles. I'm going to go through by the end of the videos to be able to solve some right triangles, as well as to solve some applied problems that involve some right triangles or some of the trig functions that we introduced last section. So let's go ahead and go over some basics of solving triangles. In general, if a question asks you to solve a triangle, it basically just wants you to determine all of the side lengths as well as all of the angle measures. So that gives us a total of 6 things we may need to identify, but obviously the problem will have to give us at least some of those 6 bits. So that'll be my goal, is basically just find whatever they have not provided for us to give us a total of 6 things that we know. So for this specific section, we're going to be talking about solving right triangles, and in general there's going to be 2 different main approaches that they'll give us. They'll either tell us an angle and a side, or they might just give us 2 sides. And each one of those will have a slightly different approach as to how we work through the problem. Now, if we have a right triangle, obviously we know one of the angles is 90 degrees, so that's 1 out of the 6 taken care of. Let's go ahead and talk about the first one, where let's say they gave us another angle, one of the acute angles. Basically, the first thing I should be able to do is figure out what that third angle is just by taking advantage of triangles having to add up to 180 degrees. Now, ultimately, we also could just take advantage of the 2 acute angles have to add up to 90 degrees, since 90 degrees is already accounted for. So the shortcut could just be subtract whatever other angle they gave us from 90 degrees, and that should give us the third angle. And now that I have all 3, I should be able to do any trig ratio for any pair of sides using SOHCAHTOA as a way that I could now find one of the sides. And then the end, once I have 2 out of 3 sides, I could utilize Pythagorean theorem if I wanted, or I could just repeat the second step, use a different trig ratio that maybe would let me solve for whatever the other side that I don't know is. Now, with all of these, I'd highly recommend you try and utilize only the given info, not any answers that you found along the way, because after all, if you use some of the answers you found along the way, if you made a mistake on that, that almost guarantees that you'll have a mistake when it comes to whatever thing you're trying to solve for using that number. So again, good rule of thumb is if you can use whatever was provided to you instead of using answers you found, that should be a little bit safer. But if you happen to be really confident in all of your work, by all means you can use previous answers you found to come up with other parts of the triangle. Now, the other situation that we have is, what if I was given just 2 sides and didn't have any angles other than the 90-degree angle that I knew? Well, at that point, we should be able to find the third side utilizing Pythagorean theorem right off the bat. And that's just basically going to either square both sides and add them together, or potentially subtract if I had the hypotenuse already. Get this third side by taking the square root of whatever that result is. And then once I have all 3 sides labeled, I should be able to, kind of similar to what we did in the previous type of problem that we would have, is pick a trig ratio that would relate 2 sides to one of the angles to solve for. And ultimately, at that point, I would have to utilize some inverse trigonometric functions like arcsine, arccosine, or arctangent, depending on which function I'm trying to cancel, to actually isolate the theta or whatever variable you might have in place of that unknown angle. And then once you have 2 out of the 3 angles, we could fall back to just subtracting from 180 or subtract the acute angle from 90, and that should give me the last angle. Or I could just pick a different trig ratio and then kind of start over, but reference the other angle that I don't know yet. Now, as far as the generic approach for how we should draw these shapes or how these problems will be presented, if you see any uppercase letters or capital letters, those always, for at least our book, will represent angles. So like capital A, capital B, capital C are going to be very common when you see those. So again, those represent angles, and then any lowercase letter will always represent sides. Now, as far as how would I draw any of these shapes, let's just maybe kind of off to the side show an example. Let's say I had a triangle ABC, and I put angle A here on the bottom left side. What I have to do is go across the shape. So notice if I were to just kind of go directly across the shape, that's where side A will always need to be. So angles and sides always do need to be opposite of one another. They should never be right next to each other. So if I continued my way around, let's say I called this top angle angle B, then across the shape should be side B, and similarly if C was in the bottom right, then across the shape should have to be C as well. So when it comes to drawing these triangles, if it hasn't been drawn for you, just always double check and make sure that you're utilizing the same letters for the sides across from their corresponding angles. Alright, so without further ado, let's go ahead and jump into our first example. So notice this one provides us with a picture. but everything has been labeled appropriately. Notice again, across from A is side A, across from angle B is side B, and across from angle C technically wasn't labeled, but I could go ahead and throw a C on that side if need be. So if we kind of look at the situation we have, we were provided with the 90-degree angle in the bottom right. They gave us this other angle in the bottom left, so I should be able to find that third angle right off the bat. So that would be the start that I would go ahead and do. Just get all three angles, since that's not too tough of a start to a problem. So with this one, I'm just going to go ahead and take advantage of, there's only 90 degrees left for the two acute angles, so if I just subtract the 61.7 that they provided for us from that 90, that should then give us a value of 28.3 for that remaining angle. And again, since that is an angle, should make sure that I include the units that I'm measuring the angle in. In this case, we're going to measure all of our angles using degrees. So now that I have that last angle, we could add that to the picture if need be, 28.3. And now I can go ahead and try and find a way to utilize the two things that were provided, or if I'm pretty confident, which I am, with the 28.3, I could utilize that if need be. But I'm going to try and just do everything using those two bits since they were provided, just in case I did do maybe some accidental typing into the calculator incorrectly, or maybe I just did some bad mental math. But anyway, if I go ahead and maybe try going after this side A, if we look at that relationship to the angle 61.7, that would be the opposite side, and then the 106.2 would be the hypotenuse. So opposite over hypotenuse, the best way to solve for A would be to set up a sine ratio. So it would be sine of that angle, 61.7, being equal to that ratio of A over the 106.2. So to solve for A, ultimately all I would have to do is multiply by that 106.2 on the other side, and that should cancel the 106.2 that's on the bottom. Notice getting the A all by itself, that's just a weird looking A, sorry about that. So if I now just jump over to a calculator and type that in, first and foremost, double check that it says degree at the top, which I am in degree mode. If I needed to switch, I would just go in here and make sure that degree is highlighted. So again, that's just the mode button right next to the second function. To get out, just second of mode where it says quit, take me back to the main screen. So I would have this 106.2, and then I'm going to multiply by the sine of the angle 61.7 that we had. Press enter, and that gives me this side length for A to be this 93.5. So if we go ahead and go back, let's go ahead and identify that answer of A equaling the 93.5. And if there were units like centimeters or inches or whatever, I would make sure to include that with it. But with this one, not really having any context to the problem, it was just here's a triangle, solve it. I don't need to worry about putting any sort of units afterward. But again, that is a length, so if there was some sort of context, I would make sure that I would put some unit afterward, such as centimeters or feet or inches or miles or whatever it might be for that context. Now if we go ahead and try and do a similar step for solving for B, I'm going to go ahead and just utilize the same two bits of info, the 106.2 and the 61.7. And this time it looks like my B is actually the adjacent, so instead of using the sine ratio, I'll just use the cosine ratio, since that's the adjacent over hypotenuse, and set it up where it would be B over that 106.2. And just like before, I would just multiply the 106.2 over to the other side. That way it cancels the denominator on the right, isolating the B. And at this point now we can go ahead and just bring the calculator back into the problem. And let's go ahead and drop that over, 106.2 times, this time cosine of 61.7. Notice this time I didn't actually press the times button. The calculator does know if you put the number right next to a function that it will just multiply. And in this case it looks like I get 50.3-ish if we go to the tenths. So I'm going to go ahead and jump back and make it 50.3. And again, whatever the unit would be what we would write down. But we've got our angle, we've got our last two sides, and then we were given two angles and a third side. So that is a total of 6 things. So I have solved everything that I could for this specific triangle. Move on to another example, this time that doesn't provide a picture. So my personal preference is each time if I don't have a picture, go ahead and just start by drawing a picture. Give myself a little bit more room, sorry about that. So for this one, let's go ahead and make our 90-degree angle here. Doesn't necessarily have to be to scale, as you can tell. I know that's going to be my 90-degree angle, so they named that angle C, so across from the shape, hypotenuse technically in this case, is going to be 23. And then let's go ahead and just call this A and B, so that means across from B, that must be where the 13 will go. So from here, it looks like I've got 2 out of the 3 sides, so I feel like the first thing I probably could figure out is just what is this side A over here, since that's across from angle A. And if we go ahead and set that up for this situation, side A should just equal, from Pythagorean theorem, the hypotenuse, since that's the longest side, squared, but then I would take away one of the legs that was provided, 13 squared, and just see what that turns into. And if I go ahead and bring that into this situation, I've got the square root of 23 squared minus 13 squared. Press enter and it gives us a value relatively close to 19. So let's just go ahead and round that to 19 units for this one. And again, if we actually had specific context that provided a type of unit, such as inches or feet, we'd make sure to include it on that answer as well. But with this one just being a generic, like here's some side lengths, no units necessary, we can just leave it as that value. So from here, looks like I've got the 90-degree angle solved for, I've got all 3 sides now solved for, so I've technically found 4 out of the 6 things. The only thing I have left to figure out is what's angle A and what's angle B. So let's just pick one and go. I'm going to go after angle A first, and I want to try and find a way to utilize the numbers that they provided, so the 13 and the 23. Looks like the 13 to me is the adjacent side. The 23 is always going to be the hypotenuse with how this was presented, so that is the hypotenuse. Best ratio for that would be the cosine ratio, so I'll just set it up as cosine of A should equal that ratio, 13 over 23. And go ahead and try and solve for A. The way I would cancel cosine is use its inverse, which happens to be called the arc cosine function. So it happens to be the second function of cosine on the calculator. So if we go ahead and bounce over to this, I've got the arc cosine on my screen. I'll type in 13 divided by 23. Since that's the ratio of my 2 sides, press enter, and it gives me a value of approximately 55.6. So if we go ahead and bounce back, this would now be a value of 55.6, and we are measuring all of our angles with triangles in this unit degrees, so just make sure that you include the degrees unit. So at this point now I have 2 out of the 3 angles, so I could just do the simple subtract that result from 90, and that will give me my last one. But in interest of practicing this idea of utilizing trig, since that's kind of what this whole chapter is about, I'll go ahead and solve it using trig. But again, there's 2 ways that we could get that last one. If I made a mistake somehow, some way, that would kind of guarantee that if I use this A of 55.6 degrees, that B would be guaranteed to be off. So again, it is a little bit safer to use the originals, but if you're confident, you can go ahead and just subtract that from 90, and that would give you the last one. But I'm going to go ahead and just utilize another trig ratio. It looks like in this case, if I change my reference to this angle B at the top, looks like the 13 now is the opposite and the 23 is a hypotenuse, so it would be more appropriate to use the sine function. So it'd be sine of that angle B is that same ratio, 13 over 23. And just like before, I'd use an inverse function for sine to cancel it, so that would be the arc sine function, or the second function of sine on the calculator, which would be the same ratio inside. And now let's go ahead and bounce over to that calculator. Second of sine gets that up on my screen. 13 divided by 23. I don't know why I just wrote 22. It should be 23. There we go. And press enter and it gives me 34.4 as my value. So 34, stay color coordinated here, 34.4 degrees. And we've got our 3 unknowns when they gave us 3 other things for a total of 6. So I do have everything checked off. And we could do a quick double check, make sure that those 2 angles add up to 90, which they do in fact do. So that confirms that we did do something correct, at least with the angles A and the angles B, since I used the trig to find them. Alright, so now at this point, let's transition to some of the application type problems that might involve these right triangles. A couple of phrases that will show up in some of these word problems are angle of elevation and angle of depression. General way of you kind of thinking about angle of elevation and angles of depression, even though they, because of parallel lines, will end up being congruent to each other, it does kind of change the appearance of how your maybe your sketch of the picture or situation might go. Regardless of what's going on, the angle of elevation and angle of depression will always start with a horizontal line. So notice here it's from a horizontal, whatever angle I go up would be called the angle of elevation, or from a horizontal line, like in this case from the plane down, that would create what's called the angle of depression. So again, easy way of thinking of these things is angle of elevation should go up from horizontal, whereas an angle of depression should go down from horizontal. You can also kind of think of like how your eye line or your line of sight would go. Normally, I guess, if you're just walking along, your eyes are probably not pointing straight up or straight down. You're probably looking straight ahead, so you kind of think like if your eyes would go up, it must be an angle of elevation, and if your eyes would go down from that, it would be an angle of depression. So we'll go ahead and work through an example of this just to kind of show how we could break down the information and solve for these two types of angles. All right, so first example here we have, kind of already have the picture drawn for us or provided for us, but we could, just by looking at what's provided, come up with our own thing. So this is kind of like two problems rolled into one. It's the two parts at the bottom. So you can kind of see, like in the picture here, there's this first triangle that's on the left that makes a 90-degree angle with vertical. And ultimately what I would need to do is just figure out what is the elevation change from the problem. So it says we're starting at an elevation of, let's see in the problem, it's 8,725. And then we go up this gondola to an altitude of 10,550. So ultimately all I would have to do is just figure out what's the difference of those two values. And that should give me the height of that specific triangle. So if I go ahead and just maybe type that into a calculator here really quick, that gets me a value of 1825 as the height for that. So maybe off to the side I'll make this a little bit clearer. I've got a horizontal and a vertical that could, let's see, I actually have the vertical is the 1825 that we had, and then we do have the ability that it traveled, or this has been identified or provided for us. It did travel a distance of 5,750, and the actual distance being traveled really is that diagonal line, so that's actually along the hypotenuse. So ultimately from here now it just wants us to figure out what would that angle of elevation be. So that should just be this bottom left angle, because that's the angle from the horizontal going up. And if I go ahead and look at what I have, it looks like I have the opposite side and I have the hypotenuse, so that should be a sine ratio. Let's go ahead and just name that theta just for the heck of it. So it'd be sine of theta should equal that ratio of 1825 over 5,750. And just like the previous example, I would go ahead and just do the inverse sine of that function or of that ratio. So 1825 over 5,750. And that should give us what the value is, which I've kind of squeezed myself out of some room, but let's go ahead and bring the calculator into the problem. It would be the inverse sine of that 1825 divided by 5,750. And that gives us a value of approximately 18.5 degrees. So 18.5 degrees for that angle of elevation. Then we have a second half of the problem where it basically says once I reach the peak, then I take a different gondola down to some other village, it looks like. So if I look at what that triangle looks like, it kind of comes over here. I could now maybe draw it more vertical right there. That's actually a better triangle to see. So we can actually maybe off to the side draw it this way, or now I'm trying to figure out what's this angle of depression. So again, it's the angle from horizontal, not vertical. And if we look at the change in elevation, it goes from, let's see, 10,550 down to an elevation of 9,500. So it seems like that would just be 1,050 as the difference of those two. So if that's 1050, and then it gives us the distance traveled as that diagonal line again of 3,913 from the story problem above, or just from the picture you can kind of see, but a lot of going on here on the kind of far right. Ultimately now I just need to figure out what is that angle, and as you can see, just like we had before, I have the opposite side, I have the hypotenuse. So once again I would use the sine ratio. Let's go ahead and name this one maybe beta just to be different. I guess it was beta in the picture as well. And let's go ahead and set up that ratio. The opposite was the 1050 or 1050 over the 3,913, and just like we did on the previous, utilize the inverse function of sine called the arc sine function, and just type the ratio that we have inside and simplify. So bring that up. I've got the inverse sine of 1050 divided by the 3913. If I remember that number right, let's just do a quick double check. 3913, that is correct. And press enter, and it gives me about 15.6 degrees for that one. And voila, we've been able to figure out those two different angles again that were all referenced from that horizontal line. It just happened to be two different triangles that I was trying to figure out Technically the angle of depression here with that second one would match this small angle, if you can kind of see what I'm doing here on the far right. That would match the angle of elevation from the mountain village to the station St. Sophia. But again, we were trying to solve for how much of the angle down I was going, so hence why it would be this 15.6 degrees, or it's the angle that's inside from the horizontal. All right, one other type of question that we can have that would potentially be a part of these types of problems is this idea of, instead of being an angle measured from horizontal, maybe having the angle being measured from the vertical. And usually, this is not always the case, but one possible way that we could do that situation is utilizing this thing that's called bearings. So bearings often are things that we could use when giving directions from a specific place using a compass as kind of our guide. So north, east, south, west would be some of the things that we would expect to see. Now, as far as how do I actually say or utilize bearings, it will always say something where it's either going to start with either north or south, so it kind of narrows down. Do I start with the top half of the vertical part of the compass or the bottom half? And then from there, it's going to give us a number of degrees that I'm going to need to go, and then a direction to go towards. So it would either be like north to the west or north to the east. So the first is always going to be like my north or south value, and then this at the end is always going to be like an east or west value. Some examples of those are kind of provided here on the picture, so just kind of glance through those. Notice again the north, I'm starting with the top half, and then 55 degrees towards west. Well, west is over here on the left, so I would go 55 degrees from that vertical towards the west, and that creates that north 55 degrees west as it's been identified. So hopefully that kind of makes sense, but the next question we'll work through basically gives us some information in that format, that being able to draw the picture, if they didn't provide a picture for us, would be kind of a key to the problem as to what angles I actually have and what I might need to use to solve an actual right triangle that's been created. Alright, so this is one such example of the idea of utilizing bearings to be able to come up with it. This picture is probably kind of tough to see, so I'm going to go ahead and just redraw it off to the side here so we can really kind of see what's going on. Or also just kind of model like how could I, from a word question, be able to draw a picture on my own. So first sentence here just basically says I have from some point A a fire that's directly south from it. So I go ahead and just put a point down, call it A, and then go directly south, and there's some other point that would be the fire. And then it says there's a second ranger point that's at B that happens to be 7.5 miles east of that first forest ranger station. So if I go to the east, that should be going to the right. So if I go to the right a little bit, that takes me to this other station B, and it says that that was a distance of 7.5 miles. I should now be able to kind of see like, okay, there's the eye line from B to the fire, and I would now need to utilize, like, here's my north, south, and if I go ahead and extend this out, east and west. Right now I can kind of look at what's my bearing from that point B. In this case it says that the bearing is start at south and it's 27 degrees 23 minutes towards the west, so that would be this angle that's outside. And what we really could do at this point is we got kind of two options: either leave it in that format of degrees in minutes, or I could convert it to decimal form if we wanted to, which we talked about in the prior video, where I would just do 27 plus this 23 over 60, or divided by 60, and then add those together, and that would turn into some decimal off to the side, which we can actually, let's just go ahead and do that. So the decimal format we could do, I just write it in the bottom right corner, 27 degrees 23 minutes is the same as doing 27 plus 23 over 60, and that gives me 27.383-ish. So I could also say this is approximately 27.383 degrees, and that might make the typing into the calculator a little bit easier. Now, because I'm rounding here, whereas the staying in minutes was actually more exact, right? This, because I'm rounding, could potentially take my answer and move it off by a little bit, but it should still stay relatively close to what the value of it will be. And we can kind of maybe see what would happen, how big of a difference is it when I type in the exact value compared to this decimal version, and just see what kind of margin of error we might have. But ultimately what we're trying to solve for is the distance from A to F. So if I just maybe put a variable in that spot, I could put X there, or technically it is across from angle B, so I could label that as side B. But for this one, since it only just wants that one answer, I can just pick whatever variable I want to use and just figure out what that value is. So if we now look at how these things are lining up, we do have a couple of parallel line situations going on. I do have the north-south line is going to be the same as this A to B line, or sorry, A to F line. So I could utilize the fact that alternate interior angles do stay identical and get 27 degrees, 23 minutes as the angle to use on the inside, and now find a way to relate those two sides. So if my 90-degree angle is here is this at this angle A, at that point I could go ahead and say that it looks like I have the opposite of this 27 degree, and I have this adjacent labeled as the unknown, so I could now set up that ratio off to the side and just say that's a tangent ratio of that angle, 27 degrees, 23 minutes, and that should equal that ratio of 7.5 over x, which we haven't really had that situation of what happens if the x is on the bottom happen all that often. But the first thing that we can do is just immediately get that x out of the denominator by multiplying both sides by it, and now it's kind of like a reset button for the problem. If all I'm trying to do is isolate the x, now what I could do is just divide the tangent over the other direction to get it back off of the x. And again, notice I'm keeping it in that exact format for this one, but we could also just be writing that as the 27.383 that we found earlier. So anyway, once we get to a point where we have the x isolated, which we just were able to accomplish by dividing the tangent over, it's just going to now be, let's go ahead and bring the calculator into the problem. So I've got the 7.5 that I had for that side length that I'm now dividing by the tangent of that angle. And since I'm going to keep it in that exact format, it's going to be the 27 degrees. So remember, that's in this angle menu, first option. And then 23 minutes, same menu, but then second option. Close my parenthesis, and now if I press enter, it gives us approximately 14.5-ish miles, 479. That seems like that's close enough to calling it 14.5 miles. So if we go ahead and go back, this is 14.5, and because of context, this time I finally get to use whatever unit it was providing, which happened to be in forms of miles. Now, if we go back and maybe see just how close this was if we would have used the decimal version of 27.383, notice the typing in, oops, I forgot my divide sign really quick. Let's just go back and insert that in. Insert divide. Notice it gives me 14.4794 instead of 4792, so still was close enough in my mind that we probably still would have made the decision to round to 14.5. So again, we could use the decimal version, or we could use the degree minute seconds. In this case, there weren't in the seconds, but we can go ahead and keep it in that exact form, and notice we still get a relatively close answer. So if you are going to do any rounding, at least kind of add a few extra decimals than maybe you normally would, just to try and prevent any sort of, I guess, rounding error mistakes that could potentially happen. But if you go out at least like to the thousandths or maybe even the 10,000ths, that should keep things relatively close, at least to the hundredths, that any rounding errors that you might have made early potentially will kind of still, because of the rounding that we might do at the end, stay close enough that we still get the same answer even if we would have kept it in the exact form. Anyway, I feel like I'm kind of rambling about that, but again, you can kind of see like we had the option to do either and we still would arrive at the same place. It just kind of comes down to, are you comfortable dealing with having minutes, or would you just rather have it be a decimal form at the very beginning of the problem and just kind of commit to it and go? Alright, so let's go ahead and discuss maybe some of the things that could happen when it comes to setting up these types of problems. The first example here we actually just kind of encountered with the last one, but again, the idea of what if I set up my ratio and my variables on the bottom, kind of utilizing that last example as my kind of basis for like what do I do in that situation. What we could ultimately do is just get that variable out of the denominator as fast as possible. That gives us now the x that's on the left side, and now look at it and go, well, now x is finally in the numerator, so what I could do is just divide by whatever it's now multiplying with, which for this example would have been the sine of 28. Again, this is just a completely made up example of just like, what if I set something up and it looked kind of like that? That's really the kind of key takeaway with this. I could then divide by the sine of 28. That now should get the x all by itself, and now it would just be whatever the ratio is of 16 to the sine of 28 degrees. And from here, just type it in the calculator. So let's go ahead and do 16 divided by sine of 28 really quick. And that gives us a value of approximately 34.1. And then from here, it would just be, what did I really solve for? Do I need to put, 34.1. Yes, okay. Would this be a degree or is this just a unit? So in this case, technically it would be, because the 28 degrees was the angle, the other two parts, the 16 and the x, must be ratios of sides. So this really would be a side length. So I would need to put a degree sign on it, even though it kind of looks like it could potentially be an angle measurement of 34. That would be kind of a reasonable thing. But it technically was a side length based on the fact that sine is a ratio of two sides. So the x was truly a side. Another example might be, let's say I wanted to use one of the other three trig functions that I haven't really used at all in this video, such as a secant or a cosecant or a cotangent. If I happen to want to do that for whatever reason, and I wanted to utilize that to maybe try and solve for an angle, really the first thing we would do, since most calculators don't have the secant, cosecant, or cotangent functions, is we would automatically take advantage of the reciprocal identity and say, well, secant technically is the same as the reciprocal of cosine. So if I just took this secant function and made it its reciprocal ratio, 10/43, now that would turn into the cosine ratio for the same angle. From here, now we can do similar step to what we've done so far. To cancel cosine, I would use its inverse, the arc cosine, and go ahead and type that into our function or calculator as well. So second of cosine, and then whatever that ratio was, I believe it was 10/43, and press enter, and it gives me a value of approximately 76.6. So theta in this case would be 76.6. And again, theta, more times than not, is going to represent an angle measurement. So that's kind of my red flag of I probably should put a unit on that of degrees. So 76.6 degrees. Again, those are just a couple of situations that could potentially occur, more than likely are going to be more rare than anything else. I guess maybe this solving for x, having variables in denominator might be semi-common, but utilizing secant, cosecant, or cotangent like I did for example B here, I would just kind of recommend try and avoid that so you don't even have to worry about doing that extra step of switching back to its reciprocal. But anyway, hopefully this video has been helpful and at least giving you the bare basics of how to solve these right triangles, as well as being able to maybe kind of take apart a story problem and draw a picture to represent it and identify what things maybe we need to solve for. But anyway, as always, if you have questions or need any extra assistance, just come find me and ask me, and I'll do my best I can to address whatever the situation might be. But as always, I appreciate you taking the time watching the video. We'll catch you next time.